Hello. Today we're going to talk about Chapter 15, Random Variables. So the chapter starts off describing some games, right? Maybe you've heard of these, maybe you haven't. I sure haven't. But how do we know if it's worth it to play the game, right? How do we know if it's a low risk or a high risk? What do we do? Okay, that's what this chapter is about. How do we assess expected outcomes? So first we start with some definitions, right? All right, first we need to assume the outcome of a random event. We usually use a capital letter for, either X, Y, or Z. It really doesn't matter. If you want to talk about a particular value, then you use the corresponding lower letter, okay? Now, there are two types of random variables. You can have either discrete or continuous. So think of discrete as something that you count, okay? So they're going to be like your whole numbers, all right? Continuous would be, you measuring height. You can get a whole bunch of different values, okay? You can mark it down to the centimeter, and you can get a bunch of in-betweens is what I'm getting at, okay? So there's just a lot more outcomes with continuous. As always, it's easier with an example. So here we have a probability model. So for an insurance company, okay, an insurance policy, the payout would be your probability. Okay, so we use a big X for any kind of payout. Now the probability of a particular payout, so payout with disability or death or neither, is here. Okay, so here, this is how much they pay for a death, this is how much they pay for a disability, and if nothing happens. Okay, and this is the chances of that happening. Okay, now this is great if we want to know the outcome of one thing, but what if we want to know how it affects us in the long run, right? What are the chances of, this affecting me, this whole insurance policy? What's their payout just in general? Okay, that's what we're trying to figure out. So we need to find the expected value. So this is kind of what you'd expect, at least what I kind of expected. You would take the outcome, all right, times the probability that it would happen, and you would add up every possibility, okay? And that would be how much the expected outcome would be. Okay, it's better with examples. Okay, so let's go back to our car insurance policy. So here it is written in words, and here's our probability chart. So if we want to find the expected outcome, all we would have to do is this. Okay, so I know that looks a little different than how the formula was written, but it's exactly the same. Okay, so we do the payout. So how much they pay for a death would be 10,000 times the probability that that would happen would be 1 out of 10,000. 1,000. And then plus, because we did sigma, all right, the payout for disability is 5,000. That probability is 2 out of 1,000. And then here, paying out nothing times that probability, which is the rest of it, 997 out of 1,000. All right, and this is the same thing, it's just written as one fraction, right? Because they're all dividing by the same number, they wrote it as one fraction. So don't let that confuse you. This is what they did, okay? That's the same thing. All right, so then once you figure that out, that comes out to 20, which is $20 per policy. Okay. Now, what if they charged $50 per policy? Well, if they're paying out about $20 per person, then they're making $30 per customer. That's not bad. Okay. So insurance is a really big money-making scheme. It's extremely helpful. I recommend everybody has it. But yeah, it can have some pretty large margins. All right, so we did center, so of course now we have to do the spread of the data. So that would be the standard deviation and the variance. Know your notation because they're going to give you formulas, so you want to make sure you know how to get it. So for variance, you want to have every value minus the mean squared. So every difference squared times the probability outcome, or I'm sorry, times the probability of it happening. Okay, and you add all those up. That's your variance. Of course, standard deviation is just the square root of that. Okay, so know that. All right, so now going back to our insurance example. So here we have our chart again, and remember, your expected outcome was 20. So this is what we do here. We plug it in. Okay, so that would be our average. The payout minus the average, you get a new value. So to find the variance, it's very easy to show your work. Okay, so we square each of those times the probability and add up each one individually. Okay, so the variance is this. So then to get the standard deviation, all we would have to do is take the square root. So now, when you think about it, okay, if our average payout is $20, the standard deviation is $386 in both directions. Okay, so let's see, that's what, negative 366 to positive 400. So remember, 60-something% is going to fall within that. Okay, all right, so know that. That kind of shows our spread, okay, and where we might, how much money we might lose or not, okay. All right, since probability is a little tricky, let's do an example. So here we have love and expected values. So here we've got it right around Valentine's Day, perfect timing. You have a waiter that brings this to a couple, okay. Black ace, they owe the full amount. Ace of hearts, they get a $20 discount. Ace of diamonds, they get to pick one more card. And now if they earn an extra, now earning a $10 discount for finding the ace of hearts. So not as much finding it the second go round. Okay, so you have 4 aces and you got to pick one. Based on the probability model, based on a probability model, let's find the expected discount. So first, design your model. All right, I made something like this. So you have your ace of hearts, a diamond, and then an ace of hearts, and then a black ace. Okay. Now, in case you're wondering where I got these probabilities from, okay, well, an ace of hearts, hopefully that's pretty easy because you had 1 out of 4. All right, the odds of pulling an ace of diamonds is 1 out of 4, but then pulling an ace of hearts, well, I only have 1 ace of hearts, but now I have 3 cards to choose from. And I want this and this to happen, so I'm going to multiply. So we get 1/12. Now, a black ace I can get on the first try or on the second try. I don't want to figure out both of those probabilities, so let's just subtract these. Do 1 minus 1/4 minus 1/12. Do that on your calculator or work it out, but that's how you can get your 2/3. Okay? Hopefully that makes sense. So to find the expected outcome, all we would need to do is our formula. So the x, okay, the cost for you times the probability. Okay, so your estimated savings is about $5.80. Now let's find the standard deviation. Okay, knowing that the expected average discount is $5.83. So remember, you subtract, square, do all that good stuff. Okay, this is an easy way to show your work. There's not that many probabilities here, so understand the formula and how to write it out. Okay, that's the standard deviation of the discounts. I'm sorry, ooh, that's the variance. So the square root of that would be the standard deviation. So this would be the standard deviation. All right, next one. So now let's change things up. Okay, so imagine the same scenario from before with the couples. Now, suppose they now have a coupon that they bring in that's also worth $5 off any one meal. So they can also use this coupon. Now, how does that affect your mean and your variance? Well, here's the formula. Okay, notice that the expected outcome increases by whatever amount. So we were getting a $5.83 discount. Now an additional $5 is going to increase an average savings of $10.83. It's not going to affect the variance. Okay, since I moved every value up $5, my variation of the numbers doesn't change. Okay, think about every person standing in a line, like in a number line, and then I told you all to go 5 units to the right. I didn't change your distance from each other. I just changed where you stood in line. Okay, does that make sense? Anyway, all right. Okay, so now what happens if we multiply? Okay, also the same thing as dividing, right? It's just multiplying by a fraction. Okay, so we're covering all our bases here. So now we're multiplying. All right, when two couples dine together, all right, they can double the discount offer. Okay, so now how does that affect the mean and the standard deviation? Well, we can write it out this way. So it would kind of make sense that the average would also be multiplied by that same amount. Okay, so since it's being doubled, that'd be times 2. So now our average savings is $11.66. Now our variance is also going to change. Okay, so notice here we have to take the previous variance and multiply by that that constant we're multiplying by, and we have to square it. Then to put it in the standard deviation, we take the square root. So essentially the standard deviation is being multiplied by that amount. Okay. All right, so now what if we had several things happening? So what if I had one restaurant discount, and then I also had a second restaurant on the other side of town with a different coupon or a different thing. Okay, so they had a different savings. If I wanted to see what my average of the day would be, I would add or subtract as I would, right? If I wanted to see what the sum of the two, then I would do the sum of the expected values. If I wanted to see the difference between them, I take the difference. Okay, so when I'm doing the average of two different stores, I can do the same thing with their expected outcomes. However, the variance, okay, since the variance is always measuring how far apart numbers are, okay, I don't care if you're going to the left or right. I'm just still changing the distance. So the variance is always addition. Okay, it doesn't matter what you did with X and Y. Okay, how we're seeing, if we're seeing the sum or difference between two different restaurants, the values of the difference, the change. I'm getting wordy and I'm kind of repeating myself here, so I'm just going to stop. Okay, variance is always sum. That's what you want to know. Okay, so let's do an example. So here we've got we've already determined this part, right? We've seen if they've doubled it. Well, now some couples decide to separate their checks and pull their two discounts. Okay, so just two couples dining separately, or doubling the discount if they sit together. Okay. So first, let's look at the expected outcome. Okay. So first, it doesn't really matter whether they dine separate or together. Okay, because we're trying to figure out what happens when they dine together, when they double the, when they combine their checks, okay, for the $5.83. So if they combine their checks, that's a savings of $11.66, which is the same as getting the double discount, okay? But the variance is going to change, okay? So the variance, we're going to have to do this, okay? So we're going to take, I guess I covered up too soon, or uncovered too soon, but that's all right. Here, we add the variances. So it was, let's see, standard deviation of $8.62. We square them, we add them. Square root it, standard deviation's different. Okay, so there's a bigger spread if I add my my checks together. So there is a difference. Okay, it does matter whether or not we pay separate or together. It's an average savings is the same, but the probability of getting close to that changes. Okay, so hopefully you've caught on that I keep talking about variance more than standard deviation because, again, standard deviation is best when explaining data, while variance is best when actually doing math. It's much easier to just say you add the variables. You add the variance. All right, if you say the standard deviation of 2, then I have to square this one and square this one, and there's just a whole bunch of extra stuff, right? And mathematicians are lazy, and they don't want to put that extra square. So we talk about variance. All right? All right, so let's do another example. So now we've got a competing program. So customers earn discounts on their meals. Now, the average discount with this is $10, standard deviation of 15. How much more can you expect to win with this second restaurant? Win or have off, whatever you want to call it. So, expected outcome, first thing we do, we subtract them. So, we're expected to make $4.17 more. Okay, notice which one I subtracted first. I did $10 minus $5.83. Okay, because I wanted to see how much I was getting at the second restaurant. Now, we do the variance. Okay, much easier to look at, well, standard deviation, ideally the variance. So we add those, take the square root, standard deviation is $17.30. So we can conclude this. They will average $4.17 more cents of a savings with a much larger spread. Okay, which can be interpreted a bunch of different ways. Well, a few different ways. Okay, what about another one? Okay, so what happens in a series of outcomes? We've talked about a savings on just one person, okay, which is great to know if you're the customer. However, if you're the owner, you'd much more want to know what you're losing throughout the day, right? So you look at your restaurant, you see how much you serve normally. Okay, what if I serve 40 couples? What am I going to give out? Okay, so first, we can do the expected outcome. So essentially, every single person is averaging $5.83 of savings. So you keep adding that up 40 times. Hopefully you realize that's just 40 times $5.83, you know. But here we get our expected outcome, okay? So I know it's a lot of words or a lot of written out, all right, but it's really just basic math. Now to do our standard deviation, we have to talk about variance. We add up all the variances. Remember, you square the variance, or you square the previous standard deviation. So $8.62 squared, add it up 40 times, or multiply it by 40. Then take the square root. There you go. So the owner expects to give out, or take a loss of $233 with a standard deviation of $54. Okay, so most likely he will be within one standard deviation, right? Think about that. So that's the loss between 180 and about 280 something, 290. Okay, most likely he will lose some money between there. That's how you would think about it. Okay? All right. So I went a little bit further in my explanation, but that's the importance of it, right? Going a little bit further is the importance of statistics and probability. Okay? Make sure you know how to interpret everything. So we talked about discrete. Now we get to talk about continuous. So remember, these are your variables that can take on a whole bunch of different values. Okay? We can't find the probability of just one event happening. You know, like if I had a class, if I was measuring the heights of all my students, what is the probability that a student will be exactly 5 feet 4 inches? That probability is really difficult to find because there's so many different options, right? So we're not going to worry about calculating a single value, okay? But we can work with models within parameters, okay? And that's good news. It's everything we've been doing with discrete can be used for continuous, okay? Because when two independent continuous variables, they have normal models. So does their sum and difference. Okay, so it's better with examples. Now with this example, all right, we are packing materials or whatever. It follows a normal model, mean of 9 minutes, standard deviation of 1.5. Now the boxing stage, so putting it in the package and boxing it up. So boxing is also normal with a mean of 6 minutes, standard deviation of 1 minute. So it's a little bit faster to box it up. So what's the probability that packing 2 consecutive systems takes over 20 minutes? All right, so let's think about this. All right, the probability of the first one is time for packing the first system. Probability of 2, time for packing the second. T is the total time to pack 2 systems. All right, we're packing one item and another item. Now, again, we have to assume 2 things. We have to have a normal model. Both of them are followed normal models, which they do. And we can assume that packing times are going to be independent, right? Packing and boxing are 2 different things. They're not going to affect each other. Now, what's the expected outcome? Well, we just add the probability of both. We said packing, so we're only doing packing. Okay? Well, yeah, I guess I said that. Okay, they're both independent because I'm packing one item and I'm packing another item. So I'm not really using my boxing stage at all this time. I want to make sure that's clear. It just says packing. So 9 minutes plus 9 minutes, 18 minutes to pack 2 things. The standard deviation, we use variance. So we take the square root, 2-minute variation. Okay, now this is where the normal model comes in handy. Okay, draw a curve. We want to know the probability. Okay, again, this is a model curve. 18-minute is the average. Standard deviation is 2.12 minutes, so it's a little bit past 20. 2 minutes plus 18 is a little past 20. Is within 1 standard deviation. But we just want to know what is the probability over 20 minutes. That's this part. Everything to the right. So we can use our z-scores, little formula. Okay, the value minus the average over the standard deviation gets you your z-score. Your z-score chart gives you this. Okay, it gives you the other direction, right? It usually does the left tail, so you have to do 1 minus. Okay, especially if you use your calculator. Okay. All right, so let's tackle another problem. What percentage of the systems take longer to pack than to box? So we have packing and we have versus boxing. So first define your items. P is packing, B is boxing, and D is the difference. Okay, we're told they're both normal, and we can assume it's independent. All right, so now we do expected and variance. The expected outcome is 9 minus 6, so 3 minutes, with a variance of 3.25, standard deviation of 1.8. Now, I always draw a picture. It just makes things easier. So you draw your normal curve with the average of 3 minutes, and we want to know the percentage it takes longer to pack than to box. So packing must be bigger than boxing. All right, every time that must be true. When it's not true, this difference is 0 or less. So we have a normal curve, and we shade from 0 to the right-hand side. Okay, then we go from there. So we do our z-score, we look at our chart, we get a probability of 0.95. So 95% of the time, it should take longer to pack than to box. Some things to keep in mind is there's still models, okay? They're useful, but it's not reality, okay? Just because you have a model of something doesn't mean that's actually what's going to happen, okay? It's a prediction. If the model is wrong, so is everything else, okay? So write it out, make a chart, graph it, okay? Visualize it, okay? If you mess up the model, everything from there is just downhill, okay? Don't assume it's normal. Think about whether the normality assumption is justified, okay? Think about it. Watch out for your variables that aren't independent, okay? That's a big one. A lot of times people assume independence when it's not, okay? Keep these things in mind. All right, more things to not forget. All right, variance is what you add. You don't mess with standard deviation. Always put it in terms of variance. That's when we use math. Standard deviation is what we talk about. Variances of independent, always add. Okay, even when you're looking at the difference, you always add variances. Okay, and when you're showing your work, do not write x plus x plus x. That doesn't make sense, okay? Use different notation, okay? The first time, the second time, the third time, okay? All right, well, that's it for chapter 15. If you have any questions, come ask me in class.